Okay. Testing. Oh, what am I doing? I forgot my grade book. What's your name again?
Gabriella Head. Gabriella Head.
Okay. And Timon, okay. And I'll get the rest from Zoom. Today is the 22nd. Okay. All right. So let me proceed to what we were about to do yesterday. As I recall, we were about to look at some problems from the assignment number 5. Let me see if I can bring that up.
It was number 3.
Number 3, yeah, sorry. Okay, where am I going? Let me go here. Let me go here. And then assignments. Number 5. Download. Okay, so okay. Now what we'll be doing in number 3 is doing a series of problems where we're doing a titration and we're going to try to find out what the pH of the resulting solution is at different points of the titration. In other words, just to remind you of something that we did earlier. Okay. So if you remember, we talked about the titration curve. All right. So what we'll be looking at is, and by the way, this one is for strong acid and strong base, right? I remember we talked about the titration curve for, strong acid, weak base, weak acid, strong base, and so on. So what we'll be doing is basically doing calculations where we can find the pH at each point of a curve like this. As I said before, this is for strong acid, strong base. We're going to do the same thing for the other types of titration. So this question says, what is the pH of each solution ABC after titrating 12 mils of a 0.0500 m sodium hydroxide solution? And in A, the acid that you'll be titrating that solution with is 6 mils of a 0.200 m benzoic acid solution. And they gave you the Ka value for benzoic acid, so you don't have to look that up, all right? So the first thing I would do in this case is that I'd find a number of moles of each of the titrants, the sodium hydroxide and the benzoic acid. So to find a number of moles, let me start off with the number of moles of NaOH, right? That would be equal to the volume, which is 12.00 mils. And I will multiply that by 1 liter over 1,000 mils to convert it to liters. And then I'll multiply that by the molarity, which is 0.0500 moles per liter. And I'd work that out to see what that gives. So 12 divided by 1,000 times 0.05. And according to my calculation, this would have to be rounded out to 3 sig figs, which would be 6.00 times 10 to the minus 4 moles. All right? So that would be the number of moles of the sodium hydroxide. And then I'll do the same thing with the benzoic acid. Yeah, I think I have a copy of it here.
And one. Thank you.
And we do the same thing for the benzoic acid. So the number of moles, I'm just going to call benzoic acid BZ, right? So the number of moles of benzoic acid is equal to the volume, which is 6.00 mils, times again the conversion factor to convert it from mils to liters, and then we multiply by the molarity, which in this case is 0.200 moles per liter. So let's do that calculation. 6 times or divided by 1,000 times 0.2. And according to my calculation, this works out to be rounded off to 3 sig figs again, which would be 1.20 times 10 to the minus 3 moles. Okay, so once we do that, the next thing I'm going to do is write down the equation for the reaction between the sodium hydroxide and the benzoic acid. And the salt would be sodium benzoate plus H2O, all right? So I'm going to set up a nice table where I write down the initial values of the moles of sodium hydroxide and benzoic acid. So for the sodium hydroxide, it's 6.00 times 10 to the minus 4 moles. For the benzoic acid, it's 1.20 times 10 to the minus 3. This will be 0, and we don't need to concern ourselves with the water. So the question now becomes, what's the change? Now, this is an acid-base reaction, right? So therefore, it's going to go to completion. In other words, one of the two reactants will be a limiting reactant. And we can easily tell which one is a limiting reactant. Mr. Medina, could you write your name on this and pass it around to those who have not written their names on it? Okay, so as I was saying, right, so basically, this reaction is going to go to completion, which means that one of the two reactants would be the limiting reactant. And we can easily tell which one is the limiting reactant because of the 1-to-1 mole ratio between the sodium hydroxide and the benzoic acid, right? So which one do you think is the limiting reactant? Between the 6.00 times 10 to the minus 4 moles of sodium hydroxide and the 1.20 times 10 to the minus 3 moles of the benzoic acid. So which do you think is the limiting reactant? Exactly. So all of this will be used up, the sodium hydroxide. And because of the 1-to-1 mole ratio between these two, the moles of the benzoic acid produced or used up should be the same. I think her name is on it already. Yeah, I'll take it. Thank you. Okay, so that's basically the changes for the sodium hydroxide and the benzoic acid. And then over here on the sodium benzoate, the change here will be plus 6.0. Oh, there should be 2 zeros, by the way. 0 times 10 to the minus 4 moles, right? So at the end of the reaction, as we said before, this will be used up, so there'll be no sodium hydroxide left. And then the difference between the 1.20 times 10 to the minus 3 and the 6.00 times 10 to the minus 4 is equal to 6.0 times 10 to the minus 4 moles. And then this would be 6.00 times 10 to the minus 4 moles, all right? So basically now we have the moles of the benzoic acid and the sodium benzoate that is produced as the only two substances that will exist after you add the 6 mils of the 0.200 M benzoic acid. All right. So basically, remember now the aim of this exercise is to determine the pH, right? So how do we determine the pH based on this mixture, the mixture containing these two substances? Well, the first thing you should recognize is that this is a mixture of a weak acid and the conjugate base of this weak acid, or the salt of this weak acid, right? In other words, we're talking about what kind of mixture? What is the name given to the mixture of a weak acid and the conjugate base of that same weak acid?
A buffer mixture?
Buffer. Thank you very much. A buffer mixture is the answer. And how do we calculate the pH of a buffer mixture? There's a formula I gave you. pH is equal to pKa plus log of the concentration of the base up top. So the conjugate base would be BZ minus divided by what goes down here? Exactly, concentration of HBZ, right? So that's a formula that we're going to use to calculate the pH of this mixture. So there are a couple of things we're going to need. We're going to need a pKa. We can find that because the question gave us the Ka value, right? We're going to need the concentration of BZ minus, and we're going to need the concentration of HBZ. So let's concentrate on determining the concentration of BZ minus. That will be equal to the moles, which is 6.0 times 10 to the minus 4 moles, divided by the volume of the mixture. Now, what's the volume of the mixture? Remember, we added 12 mils to 6 mils, or 6 mils to 12 mils, doesn't matter, right? So the total volume would be 18.00 mils, which we have to convert to liters because we're calculating the molarity. So that's 1 liter over 1,000 mils. I hope you can see what I'm squeezing in there. So let's see what that gives. 6 times 10 to the minus 4 divided by 18, 1,000. Oh no, something is wrong here. Let me do this again. 6 times 10 to the minus 4 divided by 18 divided by 1,000. Okay, so the answer I got, and please correct me if I'm wrong, but for this part here, I got 0.0. Let me do that in scientific notation. I got 3.3. 3.3 times 10 to the minus 2 m, right? And then we do a similar calculation for the benzoic, for the benzoic acid, which is basically the same thing because it's a 6.0 times 10 to the minus 4 divided by, right, so this will be equal to, I don't need to do a second calculation. These two will be equal to each other. So this will be equal to the concentration of HBZ, right, the benzoic acid. So now we plug these values into the Henderson-Hasselbalch equation. pH would be equal to pKa, which is minus log of Ka, which is 6.2 times 10 to the minus 5. And then we add that to log of the concentration of Bz minus, which is 3.3 times 10 to the minus 3 m, divided by 3.3 times 10 to the minus 3 m. So basically, these two will cancel out each other. So we know what log of 1 is equal to, right? 0, right? So therefore, this will be 0. So all we have to do now is find minus log of 6.2 times 10 to the minus 5. And according to my calculation, that is equal to, so we have two sig figs here, so we need to express the answer to 2 decimal places. So the answer I got is 4.21. So that's the answer I got. Yeah, that's it. So any questions about that?
Professor,
Yes, sir.
how do we know that the NaOH was the limiting factor?
Because, here it is, right. I thought I erased it. Because it's a 1-to-1 mole ratio.
Between NaOH and HBZ?
Yeah, between the NaOH and the benzoic acid. But if you look at the initial amounts that you had in terms of the moles, you had less of the sodium hydroxide compared to the benzoic acid. So that means that the sodium hydroxide would be the one that's used up as the limiting reactant.
Then, if it's 1.2 times 10 to the -3 minus 6,
Uh-huh. Times 10 to the -4.
why does it end up being just 6 times 10 to the -4?
Yeah, that's what you get when you do that on your calculator.
Oh,
So if you do 1.2 times 10 to the -3 minus 6.00 times 10 to the -4, you get 6.0 times 10 to the -4. Yes, sir.
Why would you use moles instead of molarity?
Okay, what are you referring to?
Like,
Oh, you mean where we use moles here?
yeah.
Okay, and that's because basically you could not use molarity because we're using different volumes of the solutions. So basically what you have to do is find the number of moles first and then look at the stoichiometry of that. You can't just say 0.20 m be the initial concentration of benzoic acid and 0.20 and what's the other one? 0.050 m is the concentration of sodium hydroxide.
You also like, once you find the moles, you don't have to change it to molarity again for 18 ml. Like, you don't have to do that.
No, you don't have to. You do need a molarity to get the final pH in terms of the Henderson-Hasselbalch equation here. But yeah, you don't have to, apart from that, you don't have to calculate the moles. I mean, the molarity. Okay, any other questions? Any other questions? Yes, ma'am.
Understand how you set up the chemical equation.
Which one? Oh, you mean this here?
Yeah.
Okay, so basically, it's an acid-base titration, right? Sodium hydroxide is a base, and the benzoic acid is the acid, right? I didn't write the full formula for benzoic acid because that's not necessary. So I just use I use HBZ to represent benzoic acid. And basically, to figure out what the products are, you just take out water between them, H and OH, and then you put together the sodium and the benzoate, and you get the sodium benzoate formula, and that's it. All right?
sodium hydroxide was a strong base?
Yes, a strong base, yeah.
Strong base and a strong acid.
Well, the acid is weak, but still, the reaction is going to take place in one direction. It's not going to be an equilibrium situation. All right? Okay, any other questions about this one? Any other questions? Any other questions? Any other questions out there in Zoom? Not? Let me clear this and scroll down to the B part. So let's see what the B part says. Okay, so the B part says this time you're adding 6.00 mils of the 0.200 m acetic acid. Now, we know what the number of moles of sodium hydroxide is because we did a calculation from the first part. Scroll down somewhere. So I'm just going to write down here to begin with the number of moles of NaOH is equal to 1.20 times 10 to the -3 moles, right? Now, what we do need to calculate is the number of moles of acetic acid. I'm going to use HA to represent acetic acid. So again, like we did before, we take the volume, convert it to liters, 1 liter over 1,000 mils, and then we multiply by the molarity, which is 0.200 mole per liter. So let's see what that gives. 6 divided by 1,000 times 0.2. So I got here 1.2 times 10 to the -3 moles, all right? So again, I'm going to write down the equation for the reaction between sodium hydroxide and acetic acid, just like we did before with benzoic acid. The answer is going to be, or the products will be sodium acetate plus H2O. So again, I'm going to set up an ice table.
NaOH, it was 6.0 times 10 to the -4.
Oh, yeah, you're right. Okay, thank you. Thank you very much. 6.0 times 10 to the minus 4. Okay. So again, we're going to set up our ice table. So initially, we're going to have 6.00 times 10 to the minus 4 moles of the sodium hydroxide. Here, we're going to have 1.2 times 10 to the minus 3 moles of the, I need one more zero, of the acetic acid. We're going to have 0 here, 0 here. The change here is going to be what? Based on what we did before, what would be the change? For the sodium hydroxide, let's start off with the sodium hydroxide.
You would subtract it,
Hmm?
subtract 6.0 times 10 to the minus 4,
Mm-hmm. Oops.
the limiting reactant.
Okay, and here would be what? Same thing. And what about here? Sodium acetate.
Adding.
Mm-hmm. Plus 6.00 times 10 to the minus 4. Okay, so at the end of the reaction, you're going to have none of that. You're going to have 6.0 times 10 to the minus 4 moles. Here you're going to have 6.0 times 10 to the minus 4 moles. And again, it's going to be the same thing. The pH is going to be equal to the pKa as we saw before. pH will be equal to pKa plus log of the concentration of A minus divided by the concentration of HA. And because these two are equal, and the concentration, if we calculate the concentration of HA, is going to be equal to the concentration of A minus, which will be equal to 6.00 times 10 to the minus 4 moles over the volume. The volume would be 6 mils plus, what was the volume at the start? 12 mils, so it's going to be 18 mils just like before. 1 liter over 1,000 mils. And this is going to give you 3.3 times 10 to the minus 2. But because this is equal to this, again, these two will cancel out. So this will be equal to pKa, which is minus log of Ka, which is minus log of 1.7. This is the Ka value given, 1.75 times 10 to the minus 5. So let me see what that gives. 1.75 times 10 to the minus 5, and then log minus. So this is 3 sig figs, so I need 4 decimal places. So this is going to be 4.757. All right? And that's how that is done. Any questions about this one? Yes, sir.
The 3.3 times 10 to the minus 2.
Yes. Yeah, M. All right?
Professor, how do you
Yes, sir.
how do you get 6.0 times 10 to the minus 4 when you subtract 1.20 and then 6?
Yes, same as I showed you earlier. You plug these numbers in the calculator, this is what you get.
I thought it would just be 2 decimal points though, since they both.
Oh, well, in this case here, one can express 1.20 times 10 to the minus 3 as the same thing as 12.0 times 10 to the minus 4, right? So if you're adding subtracting 6.0 times 10 to the minus 4, that's the same thing as 6.0 times 10 to the minus 4 here. Well, this would be 2 zeros. So this here would be rounded off to 1 decimal place. So that would be 6.0 times 10 to the minus 4. All right? Okay, any other questions about B? All right, so let me clear this and move down to the C part. Okay, now in the case of C, they gave you 6 mils of butanoic acid. So, scroll down some more. Okay, so again, the number of moles of the base is the same as before, 6.0 times 10 to the minus 4 moles. But now we need to calculate the number of moles of butanoic acid. I'm just going to use HB to represent butanoic acid. So again, like before, we take the volume, convert it to liters, and then multiply by the molarity, which is 0.100 m. And let's see what that gives. 6 divided by 1,000 times 1.00. Oh, wait a minute. That should be 1.00. That should be oh yeah, that's right. Okay. My bad. All right. I don't know what I was thinking. So it's 6 divided by 1,000 times 0.1. So I got 6.0 times 10 to the minus 4 moles, right? So again, we set up our ice table. Of course, we write our equation first. NaOH plus HB to give NaB plus H2O. Initially, we would have 6.00 times 10 to the minus 4 moles for the sodium hydroxide and for the HB. So they're both the same, right? And the sodium benzbutanoate would be 0. Again, we don't need to concern ourselves with H2O. The change here, now in this case, because these two are the same, both of them will be completely used up, right? So the limiting reactant is both sodium hydroxide and butanoic acid. So the change here is going to be minus 6.00 times 10 to the minus 4 moles. Here is going to be minus 6.00 times 10 to the minus 4 moles. And here is going to be plus 6.00 times 10 to the minus 4 moles. And at the end of the reaction, what's going to happen? You're going to have no sodium hydroxide. You're going to have no butanoic acid. The only thing that you're going to have present at this point is the sodium butanoate, which would be 6.00 times 10 to the minus 4 moles. All right? So what we need to do now is calculate the concentration of the butanoate ion, and that will be equal to the moles that we just calculated here, 6.00 times 10 to the minus 4 moles, divided by the volume, the total volume. What's the total volume in this case? The initial volume was 12 mils, right? And you added 6 mils. So again, it's going to be 18.0 0 mils, convert to liters. And we work this out. So 6 times 10 to the minus 4 divided by, okay, so again, it's going to be 0.033 or 3.3 times 10 to the minus 2 m, right? So that would be the concentration of the B minus. Now the question is, how do we determine the pH based on the fact that only B minus is present? Well, the key thing you need to recognize is that B minus is a base, right? And therefore it's going to interact with the water molecules as a base. So I'm going to need more space. So can I clear all this? Can I? Or may I? That's probably the proper way of phrasing it. All right, so I'm going to clear this. And what I'm going to do now is start off with your B minus, and because it's a base, it's going to react with water this way. HB plus OH minus. All right? So now I'm going to set up another ice table where initially the concentration of the base would be 3.3, and I think actually I made a mistake. That should be 3.33 times 10 to the minus 2. That would be the initial molarity of the base. Here you're going to have 0, here you're going to have 0. The change is minus X here, plus X here, plus X, because it's a weak base. It's an equilibrium, so therefore it won't go to completion. We don't know what X is, so that we're just going to use X as the amount of B minus that reacts, right? So at equilibrium, you're gonna have 3.33 times 10 to the minus 2 minus X. Here you're gonna have X, here you're gonna have X, and then KB will now be equal to X squared over 3.33 times 10 to the minus 2 minus X. And just like before, in previous problems, we make the assumption that X is much less than 3.33 times 10 to the minus 2, so that 3.33 times 10 to the minus 2 minus X is approximately 3.33 times 10 to the minus 2. And then what we do is simplify based on this, the relationship between KB and everything else. So KB is going to be equal to X squared over 3.33 times 10 to the minus 2, which means that X is equal to the square root of KB times 3.33 times 10 to the minus 2. So we don't know what KB is because we're not given KB for the base, we're given Ka for the acid of that conjugate base. So what do you think we need to do as far as determining what KB is? I'm sorry?
KW.
KW divided by Ka, exactly, times 3.33 times 10 to the minus 2, right? And then we put the numbers in. So KW is 1.0 times 10 to the minus 14. Ka is given as 1.52 times 10 to the minus 5, multiplied by 3.33 times 10 to the minus 2, and we find the square root of all of this. So 1 times 10 to the minus 14 divided by or multiplied by 3.33 times 10 to the minus 2. And then we divide all of that by 1.52 times 10 to the minus 5. And then we find the square root of all that. And according to my calculations, this works out to be equal to 4.68, or I should say 4.7 times 10 to the minus 6 m, right? And that would be equal to X. And then what would be the next step? Now that we know what we have solved for X up to this point, what would be the next step? Sorry, dissociation. Let me squeeze that up here. Percent dissociation will be equal to 4.7 times 10 to the minus 6 m divided by the molarity initially, which is 3.33 times 10 to the minus 2 times 100%. Okay, let's see what that gives. So 4.7 times 10 to the minus 6 divided by 3.33 times 10 to the minus 2 times 100%, and that is equal to 0.014%, which is less than 5%. So assumption is okay. So now that we have done that, we can go ahead and say that since X is equal to 4.7 times 10 to the minus 6, then we can take that to be the same as the concentration of OH minus. Now remember, the question is asking for the pH. Let me erase some of the stuff here. Let me erase down here. Okay, so therefore, X is equal to the concentration, oops, again, I got it. X is equal to the concentration of OH minus, which is equal to, what was it again? 4.7 times 10 to the minus 6 m. So how do we go about getting the pH from here?
Find POH first.
So POH is equal to minus log of 4.7 times 10 to the minus 6. Let me do that. 4.7 times 10 to the minus 6 log minus, okay, so 5.33 is what I got here. All right, and then what?
Say 14.
All right, so pH is equal to 14.00 minus 5.33. And I got 8.67 as the answer. All right. Any questions about this one? Yes, ma'am.
So how come we said that B was a base?
Because B is the conjugate base of butanoic acid. HB is butanoic acid. And when you remove a hydrogen ion from that, you're going to get B minus, which is the conjugate base. And the conjugate base will act as a base when you add it to water. In other words, it's going to gain a proton from the water molecule. And what makes it a base is the fact that you have this formed when that happens. Right? So that's why we say that B minus is a base. Yes, sir.
Why did we do a second isotable?
Because after and I raised it earlier, but remember, the first ice table showed you that the only thing that will be left at this point after the reaction is complete is the B minus, right? There's no
Which is
acid. I'm sorry?
NAB.
NAD, right, exactly, right, which produces B minus, right? So there's nothing else present in the solution. So now we have to set up a next ice table to show that the B minus is going to undergo hydrolysis. It's going to react with water to form the base. So we need to set up a next ice table because it's a weak base, and therefore we have to go through the same steps that we would go through for any weak bases, right? And therefore, that's how we end up with the pH.
So anytime that are zero in equilibrium, just do a second ice table.
Yes, if you have in an acid-base titration, if all the acid and base, which are the reactants, are used up, and the only thing left is the conjugate base on the other side of the equation, then yes, you have to take that through another ice table process. Now, let me just say this. That would not be true if the acid and base were strong, because what would happen is that the conjugate base would be very weak and therefore will not react with the water, and therefore the pH is going to be 7. But in this case, we're dealing with a weak acid and a strong base, right? So you have to set it up first to see what is left after the reaction between the acid and base, and then based on what is left, you proceed to the next step, which in this case, you'd have to set up another ice table because the only thing that's left there is the conjugate base, which will undergo the reaction with water to form hydroxide ions. Okay, any other questions about this? Yes, sir.
Would it have strong acid and a strong base?
Right, if it's a strong acid and strong base, like, let me just show you a little thing down here. If sodium hydroxide is reacting with HCl, right? To give NaCl, NaCl plus H2O, right? So let's say you had, 1 mole of this, 1 mole of this, none of that, right? Then the change here is going to be minus 1 mole, minus 1 mole, and this will be plus 1 mole, right? So here you're going to have 0, 0, and 1 mole, right? So the only thing that's there in the solution at this juncture will be sodium chloride. The thing is that sodium does nothing to water. The sodium ion does nothing to water, right? The same is true for the chloride ion. When it dissolves in water, it does nothing. It does not react with the water, it just sits there. So both the sodium ions and the chloride ion will just sit there in water, which means that the pH of the solution will be 7. Because the chloride will not produce any hydrogen ion or OH minus ion. The sodium ions will not produce any H plus ion, so therefore the solution will be neutral, right? So that's why in the titration of a strong acid, strong base, I showed you that last time. Remember we said that the equivalence point is 7, right? It's neutral, right? So that's what happens in the case of a strong acid, strong base titration. But in the case of a weak acid, strong base titration, the pH of the solution is going to be above 7. This is what we discovered in this question. 8.67 is above 7, right? So that's what happens when you titrate a strong base with a weak acid. All right? Okay, any other questions before we move on? Any other questions? Any other questions? All right, let me clear this. Do I have anything else down here you can do? Let's see. Okay, we can do that yet. So let me go back to the PowerPoint. And we're going to talk about what is called the solubility product. You know what? I just remembered something. Let me go back to the assignment. I think there's one more question that you guys can do, or we can do together. But unfortunately, I placed it late in this assignment. And that is this question right here. Okay, so I'm talking about question number 9. Okay, this has to do with indicators. Remember, we talked about indicators earlier. Indicators are basically weak acids or bases, which gives different colors under different acidic or basic conditions, right? So this question is talking about an indicator, HIND. It says it is yellow in 0.1 m sodium hydroxide and blue in 0.1 m hydrochloric acid. And it says the pH range in which the color change occurs in this indicator is over the range of 3.6 to 5.2. So the first question is asking for you to write down the equilibrium equation for this indicator, right? So the indicator is HIND, right? So what would be on the other side? When this dissociates, what would be the products? My throat. Well, when this dissociates, what would be the products?
Is that,
Hmm?
is it just that disassociated?
Yeah,
Okay, so HI and D.
yeah, that's a weak acid. So what would be the products? Hmm? H plus and
Minus.
IND minus, exactly. Okay. So the next question is, now, in order to answer this question, we have to pay attention to the information provided right here. It says the indicator is yellow in sodium hydroxide and blue in hydrochloric acid. So based on that, what do you think the color of HIND is? If the indicator is yellow in sodium hydroxide and blue in hydrochloric acid, then what do you think the color of the undissociated molecule is? Okay, somebody answered online. Blue is correct. Who said that? Who said blue? Oh, Miss Richardson said blue. Okay, and that is correct. So this is blue, which means that this is what? Hmm? What's the color of IND minus? Come on, folks.
Yellow.
Exactly. Everybody understand the reason why? No? Okay. If the solution is, if the indicator is yellow in sodium hydroxide, right? That means that the sodium hydroxide is reducing the concentration of the H plus and pushing the equilibrium in that direction, right? Which means that the color of the IND minus must be yellow, right? Because the sodium hydroxide is reducing the concentration of this. Le Chatelier's principle says that the equilibrium will be shifting to produce more H plus and therefore would favor the formation of the yellow, of the IND minus. So therefore it's going to be yellow. On the other hand, if you have acid in the solution, then, and if the acid is in excess, then it's going to push the equilibrium in the other direction, favoring the formation of HIND, which means that the color of the HIND is blue because the color is blue in an acidic solution. All right? Got that? Yes, no?
So you said if the concentration of H plus, it's too high or too low?
Right, the sodium hydroxide reduces the concentration of H plus, right? Yeah, because the OH minus will react with H plus to form water, right? So therefore, it's going to reduce the concentration of H plus, which means that the system will shift to form more H plus, but at the same time, it's going to produce more IND minus. And because the solution is blue in acid, that means that the IND minus must be, yellow in sodium hydroxide. That means that the IND minus must be yellow. All right? Now, in the case of the ACL, the equilibrium is going to shift in the other direction, right? And according to the question, it's blue in HCl, which means that the undissociated molecule must be blue. Because that is what is formed in an acidic environment. So it's all about the equilibrium shift.
It's gonna shift to the left if there's a high concentration of HCl.
Yes. Exactly. Okay. So that answers the first question. The second question is, what is the pH at the transition point for this indicator? And here's a hint right here. It says that the color changes from 3.6 to 5.2. So the pH of the transition point for this indicator must be smack in the middle of that range, right? So what's the middle of that range? How would you get that number?
I didn't divide by 2.
And divide by 2. So if you add 3.6 plus 5.2 divided by 2, you're going to get 4.4. All right? So that would be the pH at that point, right? Now the next question is, what is the value of pKa for this indicator? What is Ka? Concentration of H plus times concentration of IND minus divided by concentration of HIND, right? So if you remember, I said for question C, the answer to question C, the pH is at the middle of that range. So what that means also is that the concentration of IND minus is equal to the concentration of HIND at that point, right? So if this is equal to this, they'll cancel out, which means what? What would be the pH at that point? Or what would be the pKa at that point? Exactly, the same thing as a pH at that point, which is 4.4. Okay, somebody's saying something. Okay, yes. I'm sorry for those persons out there in Zoom. I've not been paying attention to the chat, but so far you have been answering all the questions correctly. Delaney and Jasmine. All right. So thank you for your contribution. All right. So that's the answer for the D part. Any questions about that? Yes, sir.
So IND equal to HIND.
Because that's the point where you have the transition from one color to the other, which is smack in the middle of the range that they gave you. Right? So at that pH equal 4.4, that would indicate that the concentrations of the weak acid and the conjugate base are the same. And therefore they will cancel out here, here and here, which means that the pH would be equal to the pKa at that point. The pH at that point would be equal to the pKa. So that would be 4.4, all right? Okay, let me clear this. and scroll down. Okay, so the question is now asking, what is the Ka of this indicator? And that should be easy. How would you determine the Ka based on the pKa value? So Ka is equal to if the pKa is 4.4, which is what we have here, right? How do we determine the Ka value? I'm sorry?
10 and then like raise it to -4.
10 raised to the minus 4.4. All right. So I think I did that already. Okay, so the answer I got is 4 times 10 to the minus 5 when I did that calculation. All right. Okay. Any questions about that? Any questions? What about F? It says at pH 2.2, the color, the indicator is the color blank, and the concentration of the undissociated molecule is either greater than, less than, or equal to the concentration of the conjugate base. Okay, so firstly, if the pH is equal to 2.2, right? What do you expect the color of the indicator to be? Now, the key thing you have to do is compare it to the pKa, which is 4.4, right? So if 2.2, when you compare to pKa, is less, so what do you think the color of the indicator is going to be? It's going to be blue, exactly. Which means that you have more of the undissociated molecule compared to the other component, the conjugate ion, right? So basically, for this part here, the undissociated molecule will be greater in terms of the concentration compared to that of the conjugate base. Okay. Then they say pH equal to 7. So what would you expect the color of the indicator to be? Compared to 4.4, 7 is what? Greater, right? So what would you expect the color to be?
Yellow.
Exactly. And that means that the concentration of the indicator is it greater than, less than, or equal to that of the conjugate base.
Should be less
Less than, exactly. And that's how that works out. Okay, very good. 11.3. Well, it's basically the same thing as 7, right? The pH is greater than 4.4, which means that the color here is going to be yellow as well. And again, this would be less than that. All right, so that's the same answer. Now at pH 4.4, what would you expect the color to be? Remember now, at pH 4.4, that's equal to the pKa, right? Which means that the concentrations of the yellow component and the blue component would be the same. So if you have both of them in the same mixture, what would you expect the color of that result to be? When you mix blue and yellow, what do you expect to get? Exactly. And in this case here, the concentration of the undissociated molecule would be equal to the concentration of the conjugate base. Okay, now this one is a bit tricky. It says at pH 4.3, what would you expect the color to be? Yes, sir. I know you say that, but one thing that I mentioned that you need to remember is that there is a range where there's going to be, how should I put this? If the pH is less than, I'm trying to think of a mathematical way to express this. Well, the question did say that the range is what? What was the range? The range was from 5.2 to 3.6, right? So basically, oh, okay, this is what I was thinking. If the pH is within the range of pKa plus or minus 1, right? Then basically it's going to behave as if the molecules are in approximately the same amount, right? So basically this is going to be green. But here, the concentration of the indicator will be greater than that of the undissociated molecule slightly, all right? So basically, if the pH falls within that range of pKa plus or minus 1, then it's still going to be a green colored solution. Once it gets outside of that range, it takes on the color of the more predominant species. You see what I'm saying? So if the pH is above, 4.4, then the color will be blue. If it's below, way below 4.4, then it's going to be, what's the other color? Yellow. And that's it, all right? So even though this is less than, it's still going to be green because of the closeness in the concentration of the different species. Okay, let me clear this. Oh, yes.
Plus or minus 1, that would be the difference.
Right, exactly. If so, the pH lies within that range, then the solution will still have an appreciable amount of both.
As 3.4 and 5.4, it would still be green.
Yeah. Mhm. Yes, sir.
Since the pH is less than the pKa, wouldn't it be that HIND is greater than the IND minus?
Oh, yes, you're right. It's going to be greater. Thank you. So this will be greater. Okay. Is it okay for me to clear this? Okay, so let me clear this. And is there anything else down here? Okay, so this one is saying in a 0.001 M nitric acid solution, this indicator is a color. So what would be the color? Now, the key thing to answer in this question is to recognize that the pH of this solution is 3. If you were to calculate pH equal to minus log of, oh, and by the way, it's a strong acid, right? So complete dissociation. So pH would be minus log of 0.001 minus log, and that would be equal to 3. So 3 is obviously less than 4.4, but it's within that range. So I would still say that the solution would be green. All right. And the same would be true in the case of this potassium hydroxide. In this case, well, actually, no, the pH would be minus log, well, this would be pOH equal to minus log of 0.001, which would be equal to 3, which means that the pH in this case would be equal to 14 minus 3, which is 11. So what would you expect the color of the indicator to be at this pH? If the pH is 11. So, oh, by the way, let me just say that this is green. And this would be greater than this, all right? So that's the answer for K. So for L, if the pH is 11, what would you expect the color of the solution to be? Would be yellow, exactly. Which means that the concentration of IND would be greater than that of the HIND, all right? And that's how that is done. Okay, any questions about that? Yes, sir.
I thought you said if it was a plus or minus 1 difference, and that's like 0.4. That would difference from 4.4.
Okay, hold on, 4.4. Oh, okay, yeah, you're right. Okay, yeah, you're right. I don't know what I was thinking. So let me clear this here. So what would be the color here? And what would be the color here then? Would be blue, right? Yeah, you're absolutely right. And this would be, this would still be greater than. All right, okay, thank you for that. Okay, my bad. All right, any other questions about this? Any other questions? Any other questions? All right, so let me clear this and then, what time is it? Okay, let's talk about solubility product. So let me go to the PowerPoint. Okay, so let's talk about solubility equilibrium, solubility product. And for those of you enrolled in my lab, we'll be doing an experiment based on that tomorrow, all right? So I'm quite sure you have learned in Chem 1, maybe in introductory or high school chemistry, that you have two broad categories of ionic compounds, those that are soluble in water and those that are not, right? So for example, sodium chloride or potassium nitrate, those are very soluble in water, right? On the other hand, compounds like barium sulfate and silver chloride are considered to be insoluble, right? And for those of you, I don't think any of you here were in my lecture, I would have provided for you, which is actually in the same tables that I've posted in Canvas. There's one table or one page of that document which contains rules for predicting the solubilities of ionic compounds in water, right? So in past classes I've had with students in Chem 1, they would have access to that and therefore they can predict based on the information provided in that table that, for example, sodium chloride is soluble in water, but silver chloride is not, right? Now, let me just say that what I just said in terms of the difference in solubilities is partially true because in truth and in fact, every ionic compound has some level of solubility in water. The only difference is that some are very, very soluble and some are medium in terms of solubility. And then you have the extreme that are very, they are soluble, but only slightly, right? So basically our discussion here will be dealing with slightly soluble ionic compounds, right? One example of this would be silver chloride. So if you take, a relatively large amount of silver chloride, dump it in some water and you stir it, not much of it will dissolve, but a few milligrams of the silver chloride will dissolve in water. And when that happens, you're going to end up with this equilibrium established. The silver chloride solid will dissociate slightly to form silver ions and chloride ions. So the concentrations of these ions are relatively small, especially when compared to the amount of silver chloride that you'd have added to it, right? So we can write down an equilibrium expression because after all, it's a system in a state of dynamic equilibrium, right? And we can write down equilibrium expression and the equilibrium constant for that expression is given a special name. It's called the solubility product constant, right? And that is equal to the concentration of Ag plus times the concentration of Cl minus. And you'll note that the silver chloride itself does not appear in this equation. Why? Because it's a solid. If you remember, we said from 2 chapters ago that solids and liquids in equilibrium systems do not appear in the equilibrium expression, right? So that you won't see AgCl present in this expression. You just see the concentrations of Ag plus and Cl minus multiplied to give you that constant, which is the solubility product constant. Here's another example. Magnesium fluoride dissociates to form magnesium and fluoride. And in this case, the Ksp would be equal to the concentration of magnesium ions times the concentration of fluoride ions squared. Here's another example, silver carbonate. It dissociates to form silver and carbonate ions, and this would be the Ksp expression, all right? Here's another example, calcium phosphate dissociates to form calcium and phosphate ions, and that would be the Ksp expression, okay? So that's what happens when you add a sparingly soluble ionic compound to water, an equilibrium will set up, and you can write down an equilibrium expression for that system. And as I said before, you will not see the solid terms here, here, or here in any of these equations because again, they're solids and do not show up. Now, based on the Ksp and based on the amount of ions that might be present initially in a solution, you can predict whether or not a particular sparingly soluble salt will dissolve, right? And it all depends on comparing QSP to Ksp. Now, Q is the reaction quotient. If you remember what that is basically products over reactants at any time. In this case, it's just simply the concentration of the products multiplied by each other, and you compare it to Ksp. Now, if Q is less than Ksp, then basically we're talking about a solution which is unsaturated. So therefore, you will not see any solid being formed in that situation. Now, if Q is equal to Ksp, we're talking about a saturated solution. And then if Q is greater than KSP, then we're talking about a supersaturated solution, which will eventually result in the formation of a precipitate, all right? So in some problems that we're going to see, we have to make predictions as to whether or not a precipitate will form. And it all comes down to whether or not Q is less than, equal to, or greater than KSP, all right? And here is a representative list of different compounds and their KSP values. And what you'll find when you look at these compounds, what's in common with all of them is that the measured or calculated KSP value is very low, right? So as you can see here, you have, I think the largest one is for lead chloride, lead 2 chloride, just 2.4 times 10 to the minus 4. And that is small enough a number. And then you have some like bismuth sulfide, which is 1.6 times 10 to the minus 72, which is very, very small, all right? In fact, I've provided for you in Canvas, let me just show you where it is, a more comprehensive list, which you'll have access to during your exams. If you go to tables, and then where it says the solubility product constants, okay, so this is the table that you'll have access to. And this is 6 pages long, so it's more comprehensive. And you'll be able to refer to this when it's needed, all right? Okay, so that's as far as the numbers are concerned. So basically, most of the calculations that you'll be involved in involve determining the molar solubility based on the KSP value, and then the other way around. If you're given a KSP value, or if you're given a molar solubility, you can find the KSP value. So let me define what the molar solubility is. It is the number of moles of solute dissolves in 1 liter of a saturated solution. Remember, the saturated solution is a solution that has a maximum amount of solute present in it. So that's the molar solubility. And then you have the solubility, which is the number of grams of the solute dissolved in 1 liter of a saturated solution, right? So the molar solubility is expressed in moles per liter. The solubility is expressed in grams per liter. So as I said before, most of the calculation would involve either starting off with the solubility of your compound, and then you'll get to KSP, or you get the KSP from the outset and you determine either the molar solubility or the solubility, right? So to get from the solubility to the molar solubility, you're going to need a molar mass. So you have to divide that number by the molar mass of the compound. And then based on the stoichiometry of the dissociation, you can determine the concentrations of each ion present, and then you can plug those into the KSP expression to get the KSP of the compound. Or if you're given the KSP of the compounds, you do the reverse. Based on the stoichiometry, you can determine the concentration of the cations and anions, and then based on that, you can determine the molar solubility of the compound, and then you multiply that by the molar mass to get the solubility of the compound in water, right? So I think we're going to see a couple of examples of this. So this question says, what is the solubility of silver chloride in grams per mil? So the first thing I would do is write down the equation for the dissociation of silver chloride, and then look up the KSP value. So you go to the table and you see the KSP given as 1.6 times 10 to the minus 10, and then you set up a nice table. Now, as far as the silver chloride is concerned, we don't need to concern ourselves with the molarity of that. So initially, you're going to have no silver ions, no chloride ions, and then the change is going to be the solubility. So if S represents the amount of silver chloride that goes into solution, then we're going to say that the change, because of the 1-to-1 mole ratio between the silver chloride and the silver, we're going to say that the change in the concentration of silver ions will be S, and because of the 1-to-1 ratio between these two, the change will be the same as well for the chloride ions, right? So at equilibrium, you're going to have S and S representing the concentrations of both silver and chloride ions, and then now we get the KSP expression for silver chloride, and we plug these terms into that equation, and that works out to be S squared, right? Which means that the molar solubility of silver chloride would be the square root of KSP. Now remember, the question is asking for the solubility in grams per mil. I'm sorry, grams per liters. This will give you the solubility in moles per liters. So this is 1.3 times 10 to the minus 5, and this should be in moles per liters, or M, right? But the question is asking for the solubility in grams per liter, right? So the way we do that is we take the molarity of the silver chloride and we multiply that by the molar mass. So you go to the periodic table, add up the molar masses of the silver and chlorine, you're going to end up with this, and then do your number crunching, and that would be the answer. The answer would be 1.9 times 10 to the minus 3 grams per liter. And that's basically how you determine the solubility of silver chloride in grams per liter. All right? Okay, any questions about this? Any questions? Yes, sir.
How did you get the molarity for silver and then chloride?
Because we said that KSP is equal to the concentration of those two, right? And we said that S represents the solubility. So that means that the change for the silver ions will be S, and plus S, which means that at equilibrium, the concentrations of silver and chloride will be S. So KSP will be equal to S times S, which is S squared. And then we find the square root. To get S, we find the square root of KSP, and that would be equal to the molarity of the ions, which would be the molarity of the compound itself because of the 1:1:1 ratio between the silver chloride that goes into solution and the concentrations of the ions. And then we multiply that by the molar mass to get the solubility. All right? Any other questions? Any other questions? Excuse me. All right. Okay, so we just looked at an example of determining the solubility for silver chloride, and you'll notice that you can determine different formulas of KSP based on the solubility for different ionic compounds based on the stoichiometry of their dissociation. So in the case of a situation where there's a 1:1 ratio between the anion and cations after dissociation, the relationship between KSP and solubility would be KSP is equal to S squared. We saw that to be true for silver chloride. It is true also for barium sulfate, and will be true for any ionic compound that gives a 1:1 ratio between the ions. In the case of silver carbonate, however, there's a 2:1 ratio between the silver ions and the carbonate ion. So therefore, the concentration of the silver ion will be 2S at equilibrium, and the concentration of the anion would be S. So when we plug those into this expression, we're going to end up with KSP is equal to 4S cubed, and that will be the relationship between KSP and the solubility. Or we can rearrange it. If you want to find the solubility, that would be equal to, okay, this looks like a some typo. Okay, these should be parentheses. I just realized what's happening here. Where you see this A and B here, somehow when it comes out, it came out looking like that. These are the parentheses here, right? So basically S will be equal to KSP over 4 raised to the, I think that's 1/3 power, all right? Same thing is true here. So please make a note of that. Same thing is true here. So where you see A and B, those should be parentheses. All right? So basically, based on the stoichiometry of the equation, we can come up with a mathematical relationship between the KSP and the solubility, and therefore you can solve one if you know what the other one is. All right? So it all depends on the equation of the dissociation, the stoichiometry of the equation of the dissociation. Okay, so here's a question where you're adding sodium hydroxide to a solution of calcium chloride. And the question is asking, will a precipitate form? Now, to answer this question, what we need to find basically is whether or not QSP is greater than KSP. If QSP is greater than KSP, then precipitate will form. Right? Will form. If QSP is less than KSP, then there'll be no precipitate, right? If QSP is equal to KSP, then this would be a saturated solution, which means that no precipitate would form. So saturated solution, all right? So basically, what we need to do is find out what QSP will be upon mixing the two solutions. All right? So let me just write this down. QSP. Oh, and also we have to figure out what would be the precipitate form if one is to be formed, right? So I think I have the answer here. Okay, so let me clear this here. Okay, so you add sodium hydroxide to calcium chloride. So these are the ions that would be present. So the question now becomes, which combination of ions would potentially result in the formation of a precipitate? What time is it? Okay, what combination of ions among these four that would result in the formation of a precipitate? Well, we know that sodium, when combined with chloride, will give you sodium chloride, but that would remain in solution. That will not form a precipitate, right? So the combination of calcium and hydroxide will form a precipitate, all right? You can tell that by looking at the KSP values in the tables that I've shown you, and you're going to see that there's a KSP value for calcium hydroxide, right? So that's the only possibility in terms of the solubility or whether or not a precipitate would form, calcium hydroxide, right? So now we need to find out what the concentrations are of calcium upon mixing and the hydroxide, right? So the initial concentration of calcium before mixing is 0.100 m, right? And the initial concentration of hydroxide upon mixing is 4.0 times 10 to the minus 4. Now, as far as this one is concerned, we know that because this would be equal to, let me use black. I prefer that color. Because this would be equal to 2.00 mils multiplied by 0.200 m divided by the final volume upon mixing, which would be the 2 mils plus the 1.00 liters, and that would be equal to 1.002 liters, which you'd have to convert to milliliters, which would be 1,000 mils over 1 liter, right? So basically, this is C1 V1 over V2, right? The dilution equation to find C2, right? So basically, when you work this out, you're going to get this value right here, right? Similarly, you're going to get 0.100 m when you mix the 1 liter of the calcium chloride to the 2 mils of the sodium hydroxide. So for the calcium, you're going to get 0.100 m by doing a similar calculation. Then you plug those values into the QSP equation. And when you do that, you're going to end up with 1.6 times 10 to the minus 8. Then you're going to compare that 1.6 times 10 to the minus 8 for the QSP of calcium hydroxide, which means that you have to consult the tables. I think I have the value here. Right, so the QSP is this, the KSP is this, and we notice that the KSP is larger than the QSP, or the QSP is smaller than the KSP, which means that there will be no precipitation formed because the QSP is now less than the KSP. All right? So that's basically how you can make predictions as to whether or not a precipitate will form if you have two ions coming together that could potentially form a precipitate. But first, you have to figure out what the concentrations are upon mixing and then determine, based on that, the QSP value, and then you compare the QSP value to the KSP value. If the QSP is less than the KSP, then no precipitate would form. If the QSP is greater than the KSP, then you'll have the formation of a precipitate, all right? Okay, any questions about this? Any questions? Any questions? Any questions? All right. Here's another example. Now, in this case, it says that, okay, what are we dealing with here? Okay, so you have a solution which contains two ions. One of them is the bromide ion, and the other one is a chloride ion. Both of them have the same concentration in the same solution at 0.02. Now, the question is asking what concentration of Ag, and this should be Ag plus, please make a note of that. So the question is asking what concentration of Ag plus is required to precipitate only silver bromide in a solution that contains both bromide and chloride ions, right? At a concentration of 0.02. So this is a dissociation of the silver bromide ion, and the KSP value for that is 7.7 times 10 to the minus 3. And remember now, KSP is equal to the concentration of Ag plus times the concentration of bromide. Now, if you want to find out the concentration of Ag plus that is needed to precipitate the bromide out of solution, then we have to rearrange this to get the concentration of Ag plus is equal to KSP divided by the concentration of the bromide. The concentration of the bromide is 0.02. The KSP value is given as 7.7 times 10 to the minus 3. So all we have to do is plug the numbers in, and you're going to get the concentration needed to precipitate the bromide ion, and that is the concentration of silver ions needed to precipitate the bromide ion. That would equal to 3.9 times 10 to the minus 11. Now, the question says, what is the concentration that is required to precipitate only the silver bromide? So what we need to do is find out the concentration of silver ions needed to precipitate the other ion to establish the limits of the range of concentration of silver ions needed to precipitate bromide ions. So what I've just shown you here is the equation for the dissociation of silver chloride. The KSP value, you'd have to look that up, 1.6 times 10 to the minus 10. And the expression for KSP for silver chloride is this right here. Again, just like we did here, we have to rearrange this to get the concentration of silver ions. That is equal to KSP divided by the concentration of chloride ions. And then we put the numbers in. The KSP is 1.6 times 10 to the minus 10. And the concentration of chloride ions is again 0.02. We do the math. We end up with 8 times 10 to the minus 9, right? So therefore, the answer to this question, remember now, the question is asking, what is the concentration of silver ions required to precipitate only silver bromide? The answer is that the concentration of silver ions would be greater than 3.9 times 10 to the minus 11, but would have to be less than 8 times 10 to the minus 9 m, all right? And the reason why, because we just calculated the amount that is needed to precipitate silver from, or the bromide from the solution, that's this here, and this is the amount that is needed to precipitate the chloride, which we don't want. So we know that the concentration of Ag plus must be less than this, but would have to be greater than the concentration of 3.9 times 10 to the minus 11. All right? Okay, any questions about this one? Any questions? Yes, sir.
Back one slide, I forgot to ask something.
I'm sorry?
Can we go back one slide? I forgot to ask something last.
You mean to the previous slide?
Yeah.
This one?
Yeah, what did we multiply for the KSP with when it's Ca times OH is equal to 8.0 times 10 to the minus 6?
Okay, so what about this?
How did we get 8.0?
From the tables.
Tables.
You know the same table I showed you earlier? You say you consult the table to look up
Okay,
the,
so that's a number taken from that.
right, that's the KSP, the solubility product for calcium hydroxide. Yeah, that's how you get that. Okay, any other questions? Any other questions concerning this example? Okay, moving along. Now, let's talk about something that we met before, the common ion effect. Remember, the common ion effect is basically the effect that a common ion will have on the dissociation of a particular compound in an aqueous solution. We looked at it previously in the context of the dissociation of a weak acid, but it also can apply to the type of compounds we're talking about here, sparingly soluble ionic compounds, right? So to illustrate that, let's look at this question. It says, what is the molar solubility of silver bromide in pure water and then in 0.0010 m sodium bromide? So the first part is easy to calculate because basically you're doing the same thing that we looked at before. We look at the dissociation. We say that S is the solubility of the compound. And in this case, it's a 1-to-1 ratio. So it's going to be S times S squared is equal to KSP. The KSP you can get from your tables, and then you find the square root of both sides to get S, and that works out to be 8.8 times 10 to the minus 7. So that part is the easier part. The A part is the easier part of this question. And the units here should be M, or moles per liter. Now, let's talk about the second part, the B part. In the case of the B part, you're trying to dissolve silver bromide in a solution which already has sodium bromide. Now, sodium bromide will undergo complete dissociation to form sodium and bromide ions, right? So the common ion in this case would be the bromide ions, right? So because of the 1-to-1 ratio, the concentration of the bromide ion would be the same as the concentration of the sodium bromide, which is 0.0010 m. So if we look at this dissociation again, and let's say you're adding silver bromide to the solution which contains sodium bromide, if we set up an ice table, what you'll see is that the bromide ion concentration being high will push the equilibrium to the left, right? And what does that mean? That means that the solubility of silver bromide will be less. So basically, this is the result. The concentration of silver ions at equilibrium will be S, and the concentration of bromide ions is going to be 0.0010 plus S, right? In fact, I think I prefer to show you this in the form of an ice table. So initially, the concentration of the silver ions is going to be S, and the concentration of the bromide ions is going to be S plus 0.0010 m, right? So, I'm sorry, big mistake. Initially, all right, let me just erase everything here. Initially, you're going to have 0, and here you're going to have 0.0010 m. The change here is going to be plus S, and then at equilibrium, you're going to have S. Here you're going to have S plus 0.0010 m. However, S is going to be very small compared to 0.0010 m. So that means that S plus 0.0010 m is going to be approximately equal to 0.0010 m, right? So therefore, let me do it up here. KSP is going to be equal to the concentration of silver, which is S, times the concentration of the bromide, which is 0.0010 m, which means that S is going to be equal to KSP divided by 0.0010 m. And the KSP is equal to 7.7 times 10 to the minus 13 divided by 0.0010. Let's see what that gives. Divided by 0.0010. So according to my calculation, this works out to be equal to 7.7 times 10 to the minus 10, right? So that would be the solubility of the silver bromide in a solution of sodium bromide. So if you compare this solubility here to what we did in the A part, which is here, right? You see, this is M, you see that the solubility in sodium bromide is significantly less than that in pure water. And that is basically an illustration of the common ion effect, which is that the presence of the common ion, which is a bromide ion, suppresses the solubility of the silver bromide in that solution because the presence of the bromide ion pushes the equilibrium to the left, right? And therefore reduces the solubility of silver bromide in water, all right? So that's basically how the common ion effect affects the solubility of a sparingly soluble salt in water. All right, any questions about this example? Any questions? Okay, let me see here. Okay, so as I said before, the presence of a common ion suppresses the solubility of an ionic compound, a sparingly soluble ionic compound. Now, when it comes to certain ionic compounds that are bases or acidic, then what you'll find is that the pH of the solution affects the solubility. Now, in the case of bases like magnesium hydroxide, this would be the reaction right here, the equilibrium system. the KSP value would be given by this here. And let's say you, and this is another way of expressing the KSP value. And the solubility can be calculated based on that, which is this right here, right? Now, the concentration of OH minus in this particular case is 2.8 times 10 to the minus 4 because of the 1:2 ratio between the magnesium and the hydroxide ions. So therefore, whatever the solubility is, that will be the concentration of the magnesium, and the solubility and the concentration of the hydroxide will be twice that number. All right. Now, if you had a and also based on the concentration of OH minus, you can calculate the pH of that solution. Now, let's say the pH is less than 10.45, which means that the solution is acidic, right? Or more acidic than 10.45, right? That means that the concentration of OH minus will be lower, right? Which means that basically the reason why that's low is because the H plus that is present, let's say you add acid to it, the H plus will react with the OH minus to produce water. What effect that will have on the equilibrium? It's going to push the equilibrium to the right because you're removing the hydroxide ion. The system will shift to produce more hydroxide ions, which means that the solubility of magnesium hydroxide will increase. All right? So in this case, the solubility is affected by the addition of acid to your saturated solution. That would basically increase the solubility of the magnesium hydroxide. All right? If the pH is greater than 10.45, well, we understand what's going to happen in that case. That means you're adding base to the system. So the concentration of the OH minus will increase. That will push the equilibrium to the left and therefore reduces the solubility of the magnesium hydroxide, right? So for basic sparingly soluble ionic compounds, an increase in the solubility will occur if the pH of the solution is lowered. If the pH of the solution is increased, then that means that the solubility will decrease, all right? Okay, so let me see what we can answer now in the assignment. So let me scroll down to this one right here. Oh, no, we can't answer that one. Let's go back up. Okay, number 4. It says, what is the concentration of a saturated silver 1 acetate solution? So in this particular case, first thing I would do is write down the equation for the dissociation, which would be Ag C2H3O2 dissociating to form Ag plus C2H3O2 minus, right? Initially, you'd have none of this, none of this. The change here would be plus S, where S is equal to the solubility. And then the change here would be S and S, which means that KSP is equal to S squared, which means that S is equal to the square root of KSP, which will be equal to the square root of 1.94 times 10 to the minus 3. Let's see what that gives. 1.94 times 10 to the minus 3, square root of that. So according to my calculation, this will be equal to 0.044, how many sig figs? 3 sig figs. So another 0, and this will be M. And that's how that is done. All right. Any questions about this one? Okay, so if you understand number 4, you should be able to do number 5. Can I clear this? Going once, going twice. Okay, number 5. So let me hear what you guys have to say about number 5. What would you start off by doing?
PbCl2
To give what?
would be Pb plus.
PB what? What's the charge on the lead? Plus what? Two plus two, same thing. And then the next species would be the chloride ion, because it's two of them, so 2Cl minus, right? Okay, next step. What will be the initial values for the lead and the chloride ions? 0 in both cases. And the change, if S is a solubility, excuse me. If S is a solubility, what will be the change in concentration of the lead 2 plus?
Plus S.
Plus S. And what about the chloride?
Plus 2s.
Plus 2S. All right. So at equilibrium, you're going to have plus S here. I'm sorry, not plus S, just S. And here you're going to have 2S. So KSP will be equal to the concentration of Pb2 plus times the concentration of Cl minus squared, right? So in the case of lead 2 plus, that would be S. And in the case of the chloride, that would be 2S, and that would be squared. So this would simplify to form 4S cubed, right? So KSP would be equal to 4S cubed. So that means that S would be equal to the cube root of KSP divided by 4. So this would be the cube root of KSP, which is 1.17 times 10 to the minus 5, divided by 4, which is down here. And then we find the cube root of that. So 1.17 times 10 to the minus 5. And then we do the cube root thingy. And, oh, wait a minute. 1.17 times 10 to the minus 5 divided by 4. I forgot to do that. And then do the cube root. Okay, so according to my calculations, this works out to be equal to 0.0143 M. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? Alrighty. Let me clear this and scroll down. Okay, now this one is a hypothetical situation. I've discovered a new chemical compound with the formula of A2B. If a saturated solution has a concentration of 4.35 times 10 to the minus 5, what is the molar solubility constant for A2B? So I'm assuming that A is the cation and B is the anion. If that's the case, then A2B will dissociate to form 2A plus 2A plus 2A plus plus B2 minus. All right. So initially, we would have none of these. And we know that at the end of this process, okay, let me say this. So the change here would be 2S for the A plus and the S for the B2 minus. So here you're going to have 2S and S. And it says that the concentration, which is the solubility, is 4.35 times 10 to the minus 4. So KSP for this would be the concentration of A plus squared times the concentration of B2 minus. So I'll put in 2S squared times S, which is the same thing as 4S cubed. And because we know that S is equal to this, then KSP will be equal to 4 times 4.35 times 10 to the minus 4, and then cubed. And let's see what that gives. 4.35 times 10 to the minus 4. I'll cube that. And then I'll multiply by 4. And according to my calculations, rounded out to 3 sig figs, that would be 3.29 times 10 to the minus 10. And that's how that is done. All right, any questions about this one? Any questions? Okay, let me clear this. Scroll down. Solubility product constants are usually specified for 25 degrees Celsius. How does the KSP value for a chemical compound depend on the temperature? All right, so let's think about this. What normally happens to an ionic compound's solubility in water when you increase the temperature? It goes up, right? The solubility goes up, right? So if the solubility goes up, then that means that the concentration of the ions would increase, right? So how would you expect the KSP to change? If the solubility, now remember, the KSP is equal to the product of the concentration of the ions. So for example, in the case of silver chloride, KSP is equal to the concentration of Ag plus times the concentration of the Cl minus ions, right? So if the temperature increases and the concentrations of these increases, then what happens to the KSP? It will increase as well, right? And this is mostly true. There are some exceptions, but it's mostly true for ionic compounds. So the KSP will increase with increasing temperature, all right? And that's basically what they're asking for. Okay, the next question is asking for you to calculate the molar solubility of lead to chromate. So scroll down. All right, so lead to chromate will dissociate. Let me see here. Okay, so PbCrO4 dissociates to form Pb2 plus CrO4 2 minus, right? So initially, we would have none of that, and the change here would be plus S, which means that at equilibrium, you're going to have S and S. So that means that KSP is equal to S squared, which means that S is equal to the square root of KSP. So that would be equal to the square root of 1.8 times 10 to the minus 14. So that would be equal to 1.8 times 10 to the minus 14, and then I find the square root of that. So according to my calculations, this works out to be equal to 1.3 times 10 to the minus 7 M. All right? Now, any questions about that? Any questions? Okay, keep this number in mind, all right? Now, the next part is asking for the molar solubility of the same compound in the presence of 0.020 M sodium chromate. So there are two dissociations now we have to consider. Let me clear this first. The first dissociation is the dissociation of the sodium chromate. So let me write down the equation for that. So that would be Na2CrO4, and that dissociates to form 2Na plus CrO4 2 minus, right? So because the molarity of this to begin with is 0.020 M, that means that the concentration of the chromate is also going to be 0.020 M. So the second dissociation that we have to be concerned with is the one that I showed you in A, which is the the lead-2 chromate, PbCrO4, dissociating to form Pb2 plus CrO4 2 minus. Now, because of the dissociation of the sodium dichromate, the sodium chromate, the initial concentration of the chromate will be 0.020, right? While the initial concentration of the lead 2 plus would be 0. So the change here, again, is going to be plus S and plus S, but this time at equilibrium, you're gonna have S and S plus 0.020, right? So based on what we did before, because we did an example like this before, we can assume that S is much less than 0.020, so that 0.020 plus S is approximately 0.020, which means that KSP now would be equal to the concentration of Pb2 plus times the concentration of the chromate, which would be equal to S times 0.020 equals to the KSP, which means that S is equal to KSP divided by 0.020. And the KSP from earlier is equal to 1.8 times 10 to the minus 14 divided by 0.020. And when we do that calculation, 1.8 times 10 to the minus 14 divided by 0.020. And according to my calculation, when rounded off to 2 sig figs, the answer is 9. This keeps happening. The answer, oh, I know what happened. The answer is 9.0 times 10 to the 13 minus 13 M. And if you compare that number to the previous number, what was the previous number? 1.3 times 10 to the minus 7, you see that this number is less. Again, this is an example of the common ion effect, where the presence of the common ion, in this case the chromate ion, depresses the dissociation or suppresses the dissociation of the lead to chromate. All right? Okay, what time is it? I think I'm going to stop here. Yes, I have to stop here today. All right. I'm almost finished with your tests, so you should see your results posted in Canvas. And as soon as I can, I'm going to send you back your test. And I think I have one assignment, graded assignment that I need to send back to you as well. So look out for those later on this evening. All right. So that's pretty much it. Unless there are any questions. Any questions? No questions? All right, so that's pretty much it for today, folks. I'll see you guys tomorrow at 12 noon.